So recording has been started. Not yet. Yeah, now it is started. Okay. So yeah, so one student actually asked that. So he has gone through the lectures on countability and cardinality, and he feels that most of the part or portion of those lectures are theorems and lemmas. Now he is worrying about so what kind of question will be there during exam. So I should answer of this question to all of you. Uh, See, first of all, you have to differ what is a theorem and what is a problem. So if you go through the lecture videos, which I have done also in the class, even which link I have provided you, both are same actually. So if you have gone through those, then you can see that. So there are some theorems, there are some lemmas. I agree that, and generally we do not ask the lemmas and theorems during exam. Generally we do not ask that, but that does not mean that we will not ask. But what I'm saying, we generally do not ask any theorems and any any lemmas. What generally we do ask in a exam, so we generally ask some problems. Okay, but you have to differ what is a problem and what is a theorem. For an example, means yeah, I give some if and only criteria. So that is a theorem, right? But when I give you a suppose I am doing something and where I am using them some theorem, so that is a problem. So you have to differ what is a theorem and what is a problem. Otherwise, suppose in this minor, we will ask some questions and then you will say that okay, now sir, you told us that you will not ask any theorems and now you are asking a theorem or you are asking a lemma. Okay, so you have to differ that. So if you cannot differ that, then you should read everything. So you should read all the theorems as well. But you have to differ. So what is a theorem and what is a problem? Okay. So in the last two lectures, we have done that on some theorems and problems on countability of sets. And now today we will see that cardinality. So I should share my screen. Yes. So can you see the screen? Yes.
Yes, sir.
Okay, good. So if you have any problem and if you have any doubt, you should ask. Okay. So here is cardinality. Now first we define what is a cardinality. We have already defined the cardinality of a finite set, right? So we start with that. So the cardinality of a finite set, we generally denote by this symbol. Okay, is defined by the number of elements of A. Okay, so for a finite set, we can define the cardinality as the number of elements of the set. Then, but if the set is infinite, then what shall we do? Okay, so generally, for an infinite set, we also define cardinality. And how do we define? We generally, there are many stages of infinite. We will see that. What are the stages? For an example, you can see that countable is also infinite and also you can uncountable set also. And we have already seen that a rational number q is also infinite. Real number r is also infinite. But q is countable and r is uncountable. So they are two different stages of infinity. So there are more. There are more, and we will prove that later. So the cardinality of an infinite set is used to distinguish several stages of infinity. Okay, for an example, we have seen that the cardinality of n and cardinality of r, they are different. Now we will find a relation between them. So what are the relation between the cardinality of natural number and the cardinality of real number? So for that, we define some more concept. That is, what are the relation between the stages of infinity? So definition say one. Now two sets A and B have the same cardinality. So that is this one. So if there is a bijection F from A to B, or you can say that there exists a bijection, say G from B to A. Okay, so if there is a bijection between two sets, then we say that they have the same cardinality. Okay, so that's mean this definition works for the infinite set as well as finite set. Now you can see that if you have two finite sets and if they have bijection, that's mean they should have equal number of elements, so they have equal cardinality. So it works for the finite set as well, and it works for the infinite set as well. Now there is another definition. Now if there is an injective function, okay, remember it is injective function f from A to B, then we say cardinality of A is less than equal to cardinality of B. Okay, and equivalently, it's saying that we will prove that later. Equivalently, we will say that cardinality of A is less than equal to cardinality of B if there is a surjective function say G from B to A. Okay, so we will prove this. So we will prove this today only. Okay, but for the definition purpose, I am mentioning this one as well. So if you want to show that cardinality of A is less than equal to cardinality of B, then you can find either an injective map from A to B or a surjective map from B to A. Now, what do you mean by strictly less than? That's mean the cardinality are different. Now, definition 3. Now we say cardinality of A is strictly less than cardinality of B if there is an injective function f from A to B. Oh, sorry, from A to B, but there is no bijection between A and B. Okay, so if A and B are two sets, so show that there is a injective function from A to B, but there is no bijection between A and B, then we say that cardinality of A is strictly less than cardinality of B. Now from this, can you say that cardinality of N and cardinality of R, what are the relation between them?
N is less than R.
Yes, why?
There exists an injective function, basically the identity function,
Right, we can just
but
take,
we prove that there doesn't exist bijection.
right, so we can define fx equal to x, which is injective, and why there is no bijection?
We proved it because like N is countable and R is uncountable.
Right, so we proved it, right? So therefore, this is one example. Now, what are the examples of, say, if we take rational number and R? Sorry, this is also, if we take that irrational number and R. Okay, so what are the relation between them? So obviously, we know that we can define a function f from irrational number to R. Just define fx equal to x. Now clearly f is injective, right? Now since f is injective, so therefore we can say that cardinality of irrational number is less than or equal to the cardinality of real number. Okay, we can say that. Now can we say something more? Can we say that this is strictly less than or this is equal? Yes. Any quick answer?
I feel like answer is yes, but I can't think of a bijection.
Right. So that is a difficult job to find a bijection, but you know, right? Both are uncountable. You can prove actually. So this is a trick. So how to find a, actually their cardinality are equal. So you have to find one bijection from I to R. So this is a trick. Even during exam, we can give you two sets, and we can ask that you to find a bijection between these two sets. So this is a little bit tricky. So what we can do actually? So remember, here we use, so there are many ways to define a bijection. So what I used here, so what is, so I always like that. So if you have an countable infinite set, right? If you have say two different countable infinite set, then it is easy to give a bijection between them. Just take that, say if you have a countable, infinitely countable sets, then you can list them x1, x2, xn, and say y1, y2, yn, and then you can define a bijection, say f of x1 equal to, say f of xn equal to yn. Okay. So here we will not give a specific bijection, but we will construct them. Remember, during your logic proof, we give some proof, right? So one proof is by constructive and another one is non-constructive proof. Now today here we will give a non, sorry, yeah, non-constructive proof. That's mean we are not giving one particular example. Okay. So we will not construct any example, but we will see the existence of such bijection. So first of all, what we will do, so just adopt the trick because you may need it during your examination. Okay. So what we will do, we take rational number q. Okay. We know that q is countable. Since it is countable, that implies there exists a bijection. Say f from n to q. Right? So that's mean q can be written as this one, f of 1, f of 2, f of 3, this way. Or you can say that q equal to say r1, r2, r3 in this way. So that's mean you can write q as an infinite set. And here terms are not repeated. Right? Since it is a bijection. So that's mean q can be listed as an this one. So this is an existence proof. So this exists. So now what can we do? Now see if we remove q, what is r minus q? That is irrational number. Right? So that's mean we need to, what was the question? We needed to find a bijection from I to R. Right? And if we remove q, we will get I. But we cannot remove q from here. Right? Because q is not in the subset of I. So what we will do now? We will now find one and another different set. Okay? Now, say this is a set, say A, which is R plus root 2, where R belongs to Q. Say this is my A. Now, can you say that A is countable?
Yes.
Right? So this is countable. Again, why it is countable? Then you can easily find a bijection from this set to Q. Right? Just
Can you please repeat because I got disconnected from here from the
which
R
one?
minus Q. From R minus Q is irration after that.
Okay. So what I'm saying just that if you remove that r minus q, that is a irrational number. So that's mean r is an union of irrational and rational, right? But we cannot remove this set from. So what is my plan actually? So you needed to find a bijection from I to R, right? Now what we will do? We will subtract one set countable set, and here also one countable set.
Sir, why we need to find this bijection from I to R?
Because we want to prove that the cardinality of I and cardinality of R are same.
So there, sir, but in the definition it was. Acha, acha. Okay,
Which
okay.
definition?
Okay. So I was looking at the definition 3.
No. Definition 3 says that if there is an injective function but there is no bijective function, then we will say that this is strictly less than strict B. But cardinality of I is not strictly less than cardinality of R. It is equal. So we needed to use the definition 1. So we needed to find one bijective function from A to B. Okay, so what is my plan? My plan is to from Q to R, we will remove some set, countable set. Here we will remove some countable sets, and then after subtracting those two countable sets, we will get in the left side and right side we will have the same set. Okay, and then for the same set we will define identity function only. and you remove one countable set, another countable set, and then we define a bijection there. Then we will get a bijection from I to R. So that was the trick which we will use. Now we know that Q is countable and Q can be, that's mean Q can be listed in terms of this one, but we cannot remove Q from I. Okay, because Q is not subset of I. So therefore we are refine a little bit. We refine that set Q by this set. So R plus root 2. Now this is a countable set and a subset of irrational. You can see that each element of A is irrational. Okay, now A is countable and Q union A is also countable. Right? Why Q union A is countable? Because Q is countable and A is countable. So union of two countable sets is also countable. Right? Now let A is, since it is countable, say this is my x1, x2, x3, this one. Okay? And say your Q union A, say this is, say y1, y2, y3, this. And here remember that terms are not repeated. Okay. Now can you tell me what is the relation between I minus A and Q I minus A and R minus Q union A? What is the relation between these two sets?
They're the same.
Yeah,
Right,
same.
they are just same. Right, because if we remove R from Q from R, then we will get I and then we can remove A. So they are same. So that's when we can define identity function there. Now actually we are done. Now what we can define a bijective function H from I to R. We define H of xi equal to yi for I equal to 1 to this, and H of x equal to x if x belongs to I minus A. So that's mean what we are doing actually, we have defined a function H, say A to Q union A bijection, and H your I minus A to R minus Q union A bijection. And this two gives a bijection from I to R. Now is that clear to everyone?
Sir, could you repeat how do we claim that I minus A and R minus Q union A are the same? I mean, do we just say that since I is equal to R minus Q and we are subtracting the same set, hence they are same? I
Right,
mean,
right.
we'll have to
Yeah,
prove
yeah.
that or we
That is
can
on.
claim it.
This is proved actually, na? That is same.
Sir, we can also
That
say that
is
Q and A are disjoint sets, so we can.
Q and A is disjoint, and also this is A and irrational is also disjoint. Oh, sorry. Q and I is also disjoint, and A and Q, this is also disjoint. So we can do that, right?
Okay, sir.
So what we are doing, we are just subtracting one disjoint set here and what another disjoint set here only, right? And it will be, this will be the same element. Since Q union A are disjoint, then this is actually same as Q I minus R minus Q minus A, right? And R minus Q is just I, just yeah, that is irrational number. You don't have to prove it; it is clear. Fine.
Okay, sir.
So can we say that if we remove a countable subset from an uncountable set, its cardinality will remain the same for any
Actually, yeah.
uncountable?
Yeah, you can prove it. You can prove it.
Sir, can we have two uncountable sets with different cardinality?
Yes. So that is the beauty of cardinality. We can define. So by the cardinality, we actually find many different stages of infinite. So you may have two different uncountable sets which has different cardinality.
So like one possible example could be, let's say I and 2 to the power I, like the power set of it.
Right,
And
right.
so,
Another will be power set of R. So
yes.
actually in the next lecture we will do that. We will say that for a set, say if you take natural number and if you take power set of natural number, that will be R. Okay. And then we have again power set of real number. And for a set actually X, that cardinality is always less than that power set of that set. So in this way, if you define say n and then power set of n, that is R, then we have two different cardinality. Again you apply that power set, then you will get another set which has higher cardinality. In that way, it is the stages is infinite. Okay. In fact, you can get a infinite number of uncountable sets. Means all of different cardinality. Okay, so you are getting a sequence of uncountable sets which has different cardinality.
Sir, I had one doubt.
Hmm.
You told that this thing, a 0, comma 1 to the power of n, like infinite strings of 0 and 1. You told that that is the smallest uncountable infinity.
Right.
But
No, more smallest uncountable. Right.
yeah, smallest uncountable infinity.
Huh.
So like I was thinking, so like technically we can make I can make like a at least a injective function from like inject wait no not inject yeah I can make like a function from that to every number in 0 1.
Hmm.
Like if I take this thing, if I take like 0 point and the string of zeros and ones, that will
Huh.
become a number between 0 and 1 in binary.
Huh.
And we can map, so we can map that to any to a number between 0 and 1. And if we take the function cot by x, that will map any number from 0 to 1 till to the entire real numbers. So can we say that this has the same cardinality of real numbers?
So actually, I could not catch what you are saying. So see, first of all, what do I mean by a smallest cardinality? So that's mean the cardinality of this set is same as the cardinality of R.
Okay, so R is the smallest
Right.
this thing uncountable.
Infinite. Right. And it is the same as irrational number. So all are same in this step. And the next one will be that power set of R. So since R and irrational number have the same cardinality, so we are not distinguish them. So we are not saying that irrational number has the smallest cardinality. It is smallest infinity, right? So we are just saying that R is the smallest uncountable sets. Because if you take any uncountable sets which has less number of elements, for an example, or subset of R, then it has the same, that cardinality will be same.
Sir, can we prove that R is the smallest uncountable set? Like because you're claiming it's the smallest, so can we prove that somehow?
Actually, yeah, in the next lecture I will do that. So there is a called continuum hypothesis. So something we cannot prove, that one we assume that, and that is our hypothesis. So we actually definitely cannot prove it technically, but that is true. We assume that, and all the theory goes through that one only.
Okay, sir.
Okay. So we will prove that this natural number n and this r, this is the less one, and there is no set between them, which, because if you take any set, say natural number, say x subset of r, then we will say that either x has the cardinality same as n, that's mean either x is countable or x is uncountable. Okay, so this is called a continuum hypothesis.
So how do we arrive at a conclusion that the cardinality of I and R is same? Because we are
Sorry?
defining a function. So how do
Ah,
we? So
because
because
we
we are
have defined
defining.
a bijection from I to R, so that's when they have the same cardinality.
So what we are defining by from A to Q union A and I minus A to R minus Q union A, not from I to R.
No, no, no. If you take the union of these two, so these and these are disjoint, right? And this set and this set are disjoint. So if you combine these two, you will get a bijection from I to R. Right? Suppose you have a bijection from A to B and you have a bijection from C to D. If A and C are disjoint and B and D are disjoint, then you have a bijection from A union C to B union D. Right? So this and this, they are disjoint, and similarly this and this are disjoint. So what we are saying now, take this union this, so we have I, and take this union this and we have R. So this is bijection, they are disjoint, so therefore it is a bijection function, bijective function H from I to R. And this we were defining that, right? Is it not clear?
So can you de-explain that part of H?
What should I explain?
So after that, I minus A is equal to R minus Q union A. After that,
Okay. Now after that, what we are doing actually, so see this set and this set, they are same set, right?
yes, sir.
I minus A and R minus this is a same set. So since they're same set, we just define h of x equal to x. Okay. And this is a countable set. This is a countable set. So this set was my x1, x2 dot dot dot, and this is the set y1, y2 dot dot dot. So we are defining the map h of xi equal to yi. So that's mean x1 goes to y1, x2 goes to y2, x3 goes to y3 in that way. So therefore this is also a bijection. Right? And now we know that. See, you have set, you have this set. Now this is a bijection, this is a bijection. Now so if you union this and union this, then this should be a bijection if they are disjoint. If this is a disjoint union.
Yes, sir. So how does A from function from A to Q union A is bijection?
See, this is a countable set.
Yes, sir, but the cardinality is not same, right?
Why not same? Then how do you prove that? Okay, so you know that natural number, right? You know natural number. Now take natural number minus 1. Now what do you mean? This has the least cardinality. Now you can define a bijection that n to n minus 1. You can define a bijection by h of n equal to n plus 1. Now this is a bijection, right?
Yes, sir.
But this set is a proper subset of n. But
Hmm.
still you have a bijection. So that is the beauty of infinite set.
Oh, okay, sir.
Okay, so we are not. So when we are saying that coordinate of infinite set, we are not comparing the elements. We are just taking is there any bijection or not. So if there is a bijection, then we will say that the set has the same cardinality. It might happen that both have the same different one. In the last lecture, we also proved that cube is countable, right? That's mean there is a bijection from natural number to q. There is a
Yes, sir.
bijection from natural number to q, but you know that n is a subset of q. Q has lots of many elements than n. For an example, half, 1 by 2, 1 by 3, 1 by 4, 1 by 6, anything, any number. If you find randomly m by n, if n is not equal to 1, then this is not a natural number. But still, even if you take all the negative numbers, these are not natural numbers. But still, there is a bijection. Right? Similarly, since they are countable, this is countable. So countable means there is a bijection from n to a, and countable this means there is a bijection from n to this. So we have a bijection from this to this. Right? In other words, you can say that. So natural number to a, you have a bijection. Natural number to q union a, we have a bijection. So we have a bijection from a to q minus q union a. So done.
Yes, sir. Understood.
Okay. Yeah, thank you for asking. You should ask. So if you have any kind of doubt, so don't feel shy or something like that. Okay, it might be easy. So nothing is easy.
Sir,
Yes.
for the definition of countable set, is it a if and only if condition for surjective means if x is countable if and only if there is a surjective function from n to that set? Is
What?
it if and only if condition?
So this is what was it? It was a definition, right?
No, sir, it was a lemma, I think, because we proved that in the set countability that the following two are equivalent, where x is countable and either x is phi or there is a surjective function
Right.
from
So
x
both,
to x.
if this is an infinite set, then that is a if and only if criteria. But otherwise, if it is finite, then you cannot have, right?
If it is finite, then we cannot have that if and only if condition.
Right. Because that was it was mentioned there. Because if it is finite, then you cannot have you have a surjective function from natural number to a, but you cannot have a bijective function from natural number to a. But if it is infinite, then if you have if and only, the surjective will imply also injective, bijective as well. Okay, we proved that. We proved that in the last one, in the last lecture. Okay, so can I go ahead? Okay, fine. So now, so in the green color I mentioned when I defined this one, so those two are equivalent. Now we will prove it. So these two. So if there is a injective function from A to B, so this is equivalent to a saying that there is a surjective function from B to A. Okay, so both these two are equivalent. So now we will prove that.
Sir, one more doubt. Sir, to compare the cardinality of two sets, so is it necessary that there will always exist an injective function
Right,
from one?
right. Otherwise, how can you compare?
Yes, sir. That.
So you have to find, if you want to say that cardinality of A is less than or equal to cardinality of B, then you have to define a injective function. Otherwise, you cannot say.
are there cases where we cannot say of two sets?
No. Either you have to define a bijective injective function from A to B, or you have to define a surjective function from B to A. So which we will now prove actually. So let A and B is non-empty. Then the following are equivalent. So there exists an injective function f from A to B is same as there exists a surjective function from B to A. Okay, so one implied two. So what we'll do now, first of all, let it is given that f A to B is injective. Right? It might not be surjective. Now, if we restrict the codomain, so we gave a different name, say f bar from A to f of A, which is subset of B. So this is bijective, right? So that implies we can define a map f bar inverse from FA to A, and this is also bijective. And this is subset of B, right? So what we are doing actually, so this is my say f of A, and this is say A. So we already have a bijective function from this to this, and this is B minus A, B minus f of A. So now what we'll do, you have a, this is bijective. Now how to define a surjective function from B to A? Now just choose a fixed element, this, and send all the elements to there, this point. So we are done. This is very simple, right? Now what we'll do? So choose a fixed element from capital A. Now we define function g B to A in this way that g of B will be a bar that inverse B if B belongs to f of A and equal to just the point A if B belongs to B minus f of A. So that's mean by the construction G is surjective. Is there any doubt? Or it is fine. Okay. So this is clear, right? So now remember that this is a lemma. So its proof will not be during exam, right? But if you look at the previous one, so this is not a lemma or theorem. This is a problem. So this is not a theorem. So this is a problem. So this can be in the exam. Okay. So though the proof is, you have to prove, and that proof is not very easy, but so this is not a theorem. So you have to identify what is a theorem and what is a problem. So during examination, we generally do not ask theorem. We ask problems for which you need to use the theorems and lemmas. Okay. Now to imply one. So now let G B to A be a surjection surjective function. Now we will define a function from A to B, and we need to define a injective function. Now see that since this is a surjection G, so therefore for each x from A, we have G inverse this is non-empty. You can see it is non-empty. And this is subset of B. Okay. And also for x1 not equal to x2, we have G inverse x1 and intersection G inverse x2, which is same as G inverse x1 intersection x2, that is empty. Okay. Now we can define a function. Now define f from A to B such that f of x equal to, how do you define y? What is y? Where y is an arbitrary but fixed element of G inverse x. Okay,
Sir,
so we know.
how G inverse of x1 intersection G inverse of x2 is pi, because there can be more than one element in B which map to same A. And acha, okay.
No. I'm
I'm
giving the
still
reverse
confused.
one. Reverse one. So this is a equality. So since x1 is not equal to x2, so their intersection is empty. So this, so now this equal to this, it is a set theory, and this is empty, so this is empty. Okay. And also since G inverse x is always non-empty as G is surjective, so therefore we can always choose an element and choose just that element y and fix it. So for each x we can choose a unique y. And now you can easily see that this is a injective function. Why? Now let f of x1 equal to y1 and f of x2 equal to y2. So what does it mean? So that implies y1 belongs to G inverse x1 and y2 belongs to G inverse x2. Okay. Now if x1 is not equal to x2, so that implies G inverse x1 intersection G inverse x2, so that is empty, and that implies y1 is not equal to y2. So we are done. That implies f is injective. Okay, so therefore the statements are equivalent. That means if there is an injective function from A to B, then there is a surjective function from G to A. And it is true for conversely as well. Okay. Now there is a question. Now if cardinality of A is less than equal to cardinality of B and cardinality of B is less than equal to cardinality of A, can we say that cardinality of A equal to cardinality of B? Can we say that? Do you feel it is trivial? See, here this is just infinite. And you cannot say anything for infinite set. Obviously, this is true. If A and B are finite, then this is obviously true. And this is very easy. And what if A and B are infinite?
So then we can use the lemma, right? Like if A is less than equal, cardinality of A is less than equal to cardinality of B. That means there exists an injective function from A to B. That means
Right.
there exists a surjective function from B to A.
Right.
And the next statement is implies that there exists an injective function from B to A. And since the function that B to A is both injective and surjective, that means there exists a
Why?
It not be the same function, no.
It
Oh,
cannot
okay.
may not be the same function. How can we say that it is injective and bijective?
Okay, there exists. Okay.
It is also there exists, there also there exists. So they
Yeah.
can be different.
Okay. My fault.
So now this is the stage where people start. So they do not know. So they guess that it should be true, right? Because otherwise that the theory of cardinality will not be improved if this is not true. So to extend the theory, people need this theorem. People need this. Because if it is not true, then that cardinality theory cannot be proceed. Okay, so people needed that one. So people got stuck here. Now, what the meaning of this one in terms of yeah, what is the meaning of this? This means of if A to B and there exists G, B to A, okay, are two injective function. Okay, so that's mean this is and this is true. Okay, now then there is a bijection H from A to B. Okay, so if you want this should be true, then you have to prove this one. So this theorem, and this theorem is not an easy. So this is not easy. Okay, so if there is a injective function from A to B, and if there is a injective function from B to A, then there is a bijective function H from A to B. And this is true when A and B are infinite as well. For finite it is very simple, and it is true for the infinite case. Okay, so this is a big theorem, and so to actually people prove it. So this theorem is a famous theorem. Its name is Schroeder-Bernstein theorem. So Schroeder-Bernstein theorem. So now they prove this theorem. Okay. Now this proof is very interesting. Okay. Now I will, okay. Anyway, so I can prove it. So, but anyway, so I know that this proof, the proof of this theorem will not be in exam, but you have to understand the proof because there will be many applications. For that you need the theorem. So you need the procedure how to prove this theorem. Okay. So here is the proof. Proof is very interesting. So without loss of generality, we assume that A and B are disjoint. Disjoint set. So we can without loss, we can assume that because we can take A and B any two arbitrary sets so that we have a bijection. Okay. Right. Now it is given that if A to B injective, remember that may not be surjective, okay? Because if it is surjective, then we are done. And this injective. Okay. Now what we will do? Now we will take first one element, choose say A from capital A. Now this is your A. This is your A. Now since this is A, if you apply the map F, then that will be F of A. It is in A, it is in B. Now again apply G. This will be G, F, A. Now again apply F. Now F, G, F, A. Again apply G. In this way we are going. Now this is in A, this is in B, and in so on. Now can you tell me, so this sequence, so this is an infinite sequence at the right, will it stop somewhere?
It may loop.
Right, it may loop, but it will not stop by the definition of function. Right, it may loop means after some stage some terms can be repeated. Right, but you can consider it is an infinite sequence, so it will not stop. Right, because it is a function. Now what about the left side? Now this is G. Now that is will be G inverse A. This is B in B. Now will it exist that G inverse A? Yes.
If G is bijective, then
No, otherwise it may exist. Right? It may exist for even if it is not bijective, still it may exist. But there is no guarantee that it will exist. Right? We are choosing a particular A. So for that A, it inverse may exist. Right?
So sir, we're choosing A such that G inverse A exists.
No. We are not choosing A. It is not true. We choose any arbitrary A, but G inverse A may exist or may not.
Okay, so we're assuming.
Okay. So yeah. So right. And similarly, this is in B. Now again, if we apply here F, then that will be F inverse G inverse A, and so on. Right. So ultimately, we are getting an infinite sequence in this way, but we don't know at the left it will stop somewhere or it will be an infinite sequence. We do not know. So we will give some remark here. So we will write here. Now the sequence will not terminate at right. Right? So terms can be repeated. Terms can be repeated. But the sequence will not terminate at right. So this is one observation. The other observation is the sequence will terminate at left if either F inverse or G inverse is not defined at some stage. right? And if suppose all the elements at the right and all the elements on the left exist, then again we have two possibilities. Now if F inverse and G inverse exist for all states, then we have either cyclic or we can say that doubly infinite sequence. Okay, the cyclic means all the terms at the left and all the terms at the right are same at some stage. So that's when it forms a cycle. That infinite sequence forms a cycle. Or otherwise, there is another possibility that right side is infinite, it can be repeated, but the left side may be repeated, but they are just different element. Okay, so they are the different sequence at the left and in the right, and in that case it will be a doubly infinite sequence. Okay, so we have these three cases.
Sir, what is the mathematical definition of cyclic sequence?
Cyclic means no. Here we are defining cyclic. It is not a mathematical definition. Here we are just observing this one. So these terms may not be mathematical. What by meaning of that cyclic sequence we are saying here, it forms a cycle. So that's mean you have a chain, finite chain, where it goes from this way.
Can we define this mathematically?
FG, FG, say FG. In this way, we are defining this one. You can define mathematically that as well. Say this is A, say this is F of A, G of A. So in this way, and it will be cyclic. So that's mean after some stage, all the term will be here, say X, 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 and all the terms will be X, 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 X. So therefore, we can stop at X and we will say that this is going to cyclic one. Okay. So after some stage, all the right elements are same and all the left elements are same. So that is it is a cyclic sequence.
Sir, please explain doubly infinite also with such example.
For an example, suppose this is also the right, it is suppose X, 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 and in the left it is Y, 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 Y.
Means
Then,
a single term is there on either side.
Right. So this is one possibility. So it can be any sequence.
Sir, but that too is a cycle, right?
No, no, no. That is not a cycle, right? So in the right side, suppose you are getting X, 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 X. In the Y side, it is you are going Y, Y, Y. How to make a cycle?
No, sir.
X
From
is
other
not
side.
going to Y.
Okay.
Okay, so there is no relation between X and Y. So it might happen that the left side is there are random, and then at the right also this is random. It might happen. Okay, so most of the thing is, so forget about that cyclic or double infinite. The main thing is that left hand side it is not stopping. It is, we know that, and also right in the left side it is not stopped. Okay, for that, for the particular chosen A, this is not stopping somewhere. That's mean it is the at every stage that is defined. The inverse is defined. That's all. Okay, for that particular A. Now can you observe it? So if you have now two chain, if you have now this is a chain. Now if you have another chain, and suppose that two chain has a fixed element or same element. Now can you say that whole chain are both chain are same? Did you get what I'm saying? Suppose you have two chain and those two chain has a common element. Now from this, can you say that whole chains, both chains are equal?
Yes, sir.
Yes, sir.
Yes, by the construction it is true. Why? Suppose these two are element, these two are same. So this is a long chain, this is a chain, and suppose these two are same. Now since these two are same, and say this is your A, you can name it. Now this is going to by the map F, and this is going to by the map F. Now this is another star. Now this will be same, right? Because it is a function, the same element goes to same. Similarly, that G, again this is going to same. So therefore all the elements at the right are same. And why these blue star are same? Why these blue star are same?
Should they be?
Yeah, I'm asking. They are the same or not?
If they exist, then
If
they should be same.
Why? Why they are same?
Exactly. Like there can exist two elements A, B. Oh no,
You are
wait, no,
going
wait.
to do.
G is
Injective
injected, right?
function.
Yeah, they
Okay,
are
so okay,
same.
fine. G of A equals
Now
G of B.
because G is injected, right? Now again, if something exists here, say this is F, this is F. If they exist, then again they are same because F is injected, right? So if any two elements are same, then all the chains are, the whole chains are same.
Sir, why G is injective? It should be bijective, right? Because suppose G.
Bijective? No, no, no. We assume, right? F and G are injective functions. This
No,
is
sir.
the
I'm saying like where that star has a pre-image,
no, no,
right?
no, no, no. I am not saying the star has a pre-image. If star has a pre-image, then they are same.
But sir, it can have more than one pre-image also.
No, it cannot have because it is injective, right?
Sir, it is injective in the from B to A, not from A to A, means because two elements in B can have same image, right? Two elements in B can have a same value at in A. Like if they are like we have A and B in B, B1 and B2 in B, then can
No,
then
no.
there.
See, you are confusing me. So this is A and this is B, right? And what is G? B to A is injective, right? Now this is from A. Now suppose it has a pre-image. Now if A has a pre-image, then that should be same, right?
Why they should be same?
So if A has a pre-image, then it is unique. So what is the definition of injective? Can you have 2 point x1 and x2? Both are going to A. It is the definition of injective, right? G of x1 equal to G of x2, which is A. That imply x1 equal to x2. That is the definition of injective map. No?
Yes, it was confusing a little bit.
Okay.
It's a fine thing.
Yes, I got disconnected. Fine. Can you hear me? Am I audible now?
Yes, sir.
Yes, sir.
Okay, I got disconnected. Okay. So if any two elements are same of two sequence, then all the elements will be same. Okay, so that's mean. So that's mean you can write that A union B as disjoint union of this one. Say A alpha, f of A alpha, gf A alpha, all those elements, and also G inverse A alpha, F inverse G inverse A alpha. This. So this is a disjoint element. Here, inverses can be empty after some stage, and it gives a partition. Partition of the set A union B. Right? So if we collect all the elements of this sequence, then they forms a partition. Why they forms a partition? Because if you take any two sequence, that is mean any two sets, if they have one common element, then all the elements should be same. Is that clear? They are forming a partition. Now that's mean if we exclude the elements, so A alpha equal to your all the elements, say A, okay, I can write A alpha, GF A alpha in this way, and F inverse G inverse A alpha, all the elements this, and if we write B alpha equal to the other element, which are the elements of B, G inverse F inverse G inverse A alpha, this, then A is a disjoint union of A alpha, B is a disjoint union of B alpha. Okay,
So
so
could you
they form
explain once again what is disjoint union?
where this one.
So the definition of a disjoint union, what is?
Definition of disjoint union means the sets are disjoint. So here the sets are disjoint. This is not usual union, but the sets are disjoint.
Okay. Okay.
Okay, because if you have two sets, if they have one common element, then all the elements are same. So that's when there will be the basically same elements. So here we are taking that disjoint union. So for so that's mean actually now suppose this is your A and suppose this is your B. So you have a partition actually. Says this is your A alpha 1, say A alpha 2, A alpha 3, and similarly B alpha 1, B alpha 2, B alpha 3. So this forms a partition. So you can write A as disjoint union of some sets.
Hello.
Yes.
Sir, when you have written A union B is equals to that alpha, then how can we say that in this all the elements of B will also be present? Like all elements of A will be present because alpha is element of A. How can we say that all the elements of B will be present too?
That is a good question. That is a good question. See, we have chosen here A is any arbitrary set, arbitrary one, right? Here we choose any A, any arbitrary. Now suppose you have an element of B here. Then GB will be in A. Suppose B here. Then GB in A. Right? Now you can take your A equal to GB and make the sequence. Then that B will also present there. Did you get what I'm saying?
No, sir. So can you explain once more?
Okay. Now suppose you choose any arbitrary element from B. Suppose this is this B. Okay. Then GB will be in A, capital A. Now choose that small a equal to GB. Now this is your GB. So this will be your B. So that's mean that B will be in a sequence. So in that way, you will get a sequence containing that B.
Yes, sir. Yes, sir. Got it.
Got it? So this is a good question. I missed that part. So in that way, you can say that all the elements of A and all the elements of B should present in this sequence. Okay, so therefore you have these sets in a partition. Now we define a map, say H alpha, for each partition, A alpha to B alpha. Okay, so for each partition we define this map, and then we can say that this set we can define a map from H to define this bijective for all alpha, and that imply H A to B is bijective, where H you can just take union of H alpha. Now how to define this bijective? Now how to define this bijective map? Now there are cases. Okay. Now suppose this. So this. So this is my F G F G. Okay. So now suppose this is a infinite sequence. Okay. Now if the sequence stops at A. Okay. So then define H of A equal to F of A. So just define H equal to F. And you can see that this is a bijective function. See, this element goes to this element goes to this element. In this way, you can define a bijective function. Right? So for that particular chain, you can define a bijective function. Just take H equal to F. Okay? By taking H equal to F, you will have a bijective function for that chain or for that partition A alpha. Now suppose the chain stops at B. So this is the situation. Now how to define the map H in that case? Or you can say that H alpha. Now how to define this? Yeah. Then, so this is your G, this is your F, this is your G, this is your F. Now define H in this way. So that's mean define H, say A alpha, from A alpha to B alpha. Define H of A alpha equal to G inverse A alpha. So we define H equal to just here G inverse in this way. Okay. So if the sequence stops at A, then we define H equal to F. If the sequence stops at B, we define H equal to G inverse, so that A equal to B, right? You can see that this is an infinite sequence. And if the sequence does not stop, if the sequence does not stop at left, so you can choose if either H is either F or G. Both are fine. You can either choose F or you can either choose G. So both are fine. Okay. So in this way, you can get a bijection from A to B. Okay, so you can look at one example to make it easy clear. Now, say example how to find. So I can take around 5 minutes to take the example. Now say A equal to 0, 1 and B equal to this closed interval 0, 1. Now can you give a quick bijection from A to B? So
Sir, is it okay if I give from B to A?
it is fine from B to A.
Okay. If it's of the form 1 by 2 power n, where n is a whole number, then 1 by 2 power n plus 1.
Right.
Else
Yeah,
it's
we'll do the similar. So here actually here we will see the application of the Schroeder-Bernstein theorem. Okay. So first of all, we take a bijection injective function from A to B. It is very easy to give an injective function. Just give f of x equal to say x. Okay. And give g is a injective function from B to A. Take g of x equal to x by 2 since 1 is not here. Okay. Now then f and g both are injective, right? Now by using that Schroeder-Bernstein theorem, you can give a bijection from A to B. How to find that? Now note, see, take 0. Okay, 0 belongs to A. Now where 0 goes to 0? This is goes to 0 by f g. And what is the inverse image of g? The inverse image of 0 by the g. Again, this is 0, right? So this is cyclic. Now since this is cyclic, so we can choose h either f or g, any. So now take h of 0 equal to 0. Okay. So we need to construct H a map from A to B, which is bijective. Okay. Now take 1 by 2 belongs to A. Okay. Now 1 by 2 by F, it is 1 by 2. By G, it is 1 by 4. By F, it is 1 by 4 again, and it is going in this direction. And what is the inverse image of 1 by 2? By the G. So this is 1. And what is the inverse image of 1 by F? We don't have any. Right? Because what is F? This is right. This is just 1, right? So if you choose 1, 1 does not have any preimage here. So it stops at here. Right? So this is in B. This is in A. So we define H in this way, this direction. So take, so here H of half will be 1, H of 1 by 4 will be 1 by 2, H of 1 by 8 will be 1 by 4. In this way, we are defining H. And now check that for other elements. So we have defined H0 equal to 0 and H1 by, we defined H0 and H1 by 2 to the power n for n bigger equal to 1. We have defined this. Now check that for 1 by 2 to the power n less than x less than 1 by 2 to the power n minus 1, you can check that it stops at actually in A. The sequence stop at left at A. So therefore you can choose. So you can choose H, either F or G. Or just choose. Just take H equal to F. So H of X equal to X. Now if you define Hx equal to X and this, then you have a bijection from A to B.
So can we choose H equal to F or G both? Because in the proof you told that we define H is equal to F in this case.
No, you can choose. You can choose G as well. That is also fine. Okay. So that's mean what is your final bijection? So H 0 1 0 1. That bijection will be H of X will be say 2x for x equal to 0, 1 by 2, 1 by 4 this and x otherwise. So this is your bijection. So we are doing this. For 0 it is 0. For 1 by 2 to the power n it is this way. Just multiple by 2. So you can write it is in terms of 2x. And for otherwise it will, you are just taking the element a. So that's all. So we are done.
So how do we choose the element from M? Is there we can have like many tries, to arrive at a conclusion. Like here we choose randomly 1 by 2, and then we found that for 0 we simply define s of 0 0, and for 1 by 2 to the power n we define a function. And there can be
Right,
case.
because you can choose randomly, that, but it has a procedure. Actually, if you choose, for an example, in the class notes, I did not have time, so I just keep some parts. So if you look at the class notes, you can see that I tried with 0, I tried with 1 by 2, 2 by 3, randomly few number, and you can see that pattern. You can see the pattern means if you look at 1 by 2 by 3, then you can see that where it stops at A, and whenever you have in this range, it will stop at A, and otherwise if you have this kind of elements, say 1 by 2, 1 by 8, then it stops at B. So it has a beautiful pattern. So it is easy to guess what are the ranges where you have to define F or G. So just try with few numbers, then it is easy to guess it.
So sir, like if they ask us to prove that two sets are this thing have the same cardinality, we don't have to like find the bijection, right? We just find the two injective functions. It should be enough for the test.
Right. Fine. If you find one injective function from this to this, another injective from this to this, then there must be a bijective function. Yeah, good
So
point.
if it is not asked until unless explicitly that you have to find the bijection, we
Yeah,
don't need.
but during examination we can give one sets and we can ask you to find a bijection. We may not say by using you have to use that Schroeder-Bastien theorem, but we may also say that by using Schroeder-Bastien theorem and using these two injective function find a bijective function. We can give this kind of problem as well. So you should not skip the proof. You have to just go through the proof again, and you can see that that is beautiful. And this is beautiful in the sense that it will be useful in future as well, not for this course only. Because everywhere, if you are doing some mathematics, you have to deal with these functions. So it is better to know the proof. So if you have actually any two injective function from A to B and B to A, it is interesting to find one bijective function. That is very interesting. So obviously you have to guess something because there is no algorithm to find such a function. It is little bit random. Okay, so our time is up. We should stop the meeting because maybe you have another class. So we will continue from this point on the on tomorrow, not tomorrow, the next lecture.